What is up, party people? All right, so now we are done with chapter A. We finished our first chapter of the summer semester. Woo! So now we're on chapter B. This is supposed to be B2. Factoring, is that supposed to? Factoring rational expressions. Am I on the wrong thing? Rational expressions. Factoring rational expressions. 1 second. We're on the right thing. This is supposed to say factoring algebraic expressions, and this is B2. All right, cool. Easy. Why don't you just go fix it and then re-upload it? It takes too much time. All right, cool. So we use distribution to do what is called expanding a polynomial. So with that, if I write x plus 2, x plus 3, I would distribute x plus 2 to the x and x plus 2 to the 3. So I'd have like x squared plus 2x plus 3x plus 6, and then that would give me x squared plus 5 plus 6. Some people also call that foiling. So you do the first ones, the outer ones, inner ones, and then the last ones of each factor. Okay, I wrote this last line very badly. X squared plus 5x plus 6. So going this way, expanding. And that's pretty easy, right? Just kind of like cubing something and squaring something. Going that forward direction, that's pretty easy. Going the backward direction, that's pretty hard. Cube root of 64. I have to think forward and then back. So when it comes to factoring, that actually is the reverse of expanding. So that's where I would give you a polynomial like this, and you can factor it. So that means I write it in terms of factors. Factors are things that are multiplied together. Terms are things added together. So this way is factoring. And there are lots of different ways to factor. We'll talk about them. Not every polynomial can be factored. So then we'll also talk about how to figure out if something is factorable. All right. So why is factoring useful? So this actually has like a really broad of like math in the real world explanation. It helps find roots or the zeros. So roots, I shouldn't say roots, but when we think of roots, the roots start when a plant goes in the ground. So the roots are when like x squared plus x, 5x plus 6 equals 0. So it's helpful. That's not how you spell helpful. So if you're trying to find a root of a polynomial, it's when the polynomial equals 0. All right. So I don't know how to like, and then I'll get x squared plus 5x, what equal to -6? Well, then how I have x squared and x, I can't take this, can't move the 5x over and then take a square root because I still have an x on the other side. That's just, it's not going to work that way. So but if I factor, I would get like x plus 2 and x plus 3 equal to 0. And we'll talk about something called the zero product property, which will then help us further solve this equation. Okay, but that's why factoring is very, very useful, finding roots. All right, so the first form of factoring is pretty fun, in my opinion. Factoring out common factors. So remember, factors are things that are multiplied. Bug bite on my leg. So I want to factor x squared minus 3x. So if I want to factor out a common factor, I want to look at what each term, so separated by addition and subtraction, have in common. So I have 6x squared and 3x. So each one of them has 1x. This one actually has 2 because it's x squared. So, and then 6 and 3 are both divisible by 3. So you can write 6x squared if you want to see it out as like 2 times 3 times x times, oops, my writing, times x, and then 3x is just 3 times x. So they both have in common this 3x. So I can write that x squared minus 3x is equal to 3x, and then what's left over from each of the terms. So if I pull out 3x from 6x squared, I'm left with a 2 and an x. But what about minus? I should have put a minus there. The second part, the negative 3x. Well, think about if I distribute this 3x, I can't put 0 here because 0 times anything is 0, not get rid of that term. I want a placeholder, and a really good placeholder is 1. Because 1 times anything is that anything. So that's why it would be 1. You can think of like there's always a hidden 1. Okay? So in the above example, that 3x is called the greatest common factor. We also could just refer to that as the GCF, which also reminds me of the BFG, the Big Friendly Giant. Such a good, I love Roald Dahl. Great writer. It's the biggest thing that both terms share, right? So 3x. We can't just say 3, that is definitely a common factor, but I can pull out more from each of the terms. Okay, let's make sure I was recording. So now I can do what's called factor via grouping, and that takes factoring out common factors and uses it on bits of polynomial, and we'll show you because that makes no sense. So we can factor the same polynomial by grouping and pulling out greatest common factors. So I'll group a few terms together, usually 2, and I'll pull out the greatest common factor, and then I'll have another 2 terms of there, and I'll pull the greatest common factor. Okay, so it's best to use when we have 4 terms. So this is a really great way to factor trinomials. So when the highest power is 3, we usually also refer to, if it's like squared, it's a binomial, I think. It's just best to use for 4 or more terms. So we're asked to factor the following expression via grouping. Okay, so what we're gonna do is usually the problem set up where you can just choose the first 2 and then the second 2 to group together. So I like to say the green group and the orange group. We'll do like these rustic Miami colors. Right, so x cubed plus x squared plus 3x plus 3. This is the same thing as we wrote before. I'm just adding these parentheses more as a helpful thing to group them together. Because in this situation, the parentheses aren't really distributing any multiplication, but they're just kind of telling us where our groups are, but not hurting the equation at all. So that's why they're okay. We need to be careful when there's a negative here though, but we don't have that, so we won't talk about that quite yet. Okay, so and I'm now going to pull out the greatest common factor of each of these little groups. Okay, so let me redraw my green and my orange. All right, so x cubed and x squared, this has x times x times x, and this is x times x. So the greatest common factor is x squared. So this x cubed is going to be left with x, and then x squared, all that's going to be left when I pull out x squared is just 1. You can think about it as I'm dividing x squared by x squared. So I'm going to be left with just a 1. That's what you mean by pulling out a factor, is I'm dividing it. So I'd be like dividing by x squared, divided by x squared. The x squared comes out, and that's how I get x and 1. All right, cool. So now in the next one, 3x plus 3, my greatest common factor is 3. Good job. And again, I'd be left with just x plus 1. Great. So now I have something multiplied by x plus 1 plus something multiplied by x plus 1. Right, so I want to read it as x squared, x plus 1 plus 3, x plus 1. So now I have these two big terms. I have the green one and the orange one. Just like I had 6x squared and 3x squared. Something plus something else. Each of these has an x plus 1 in it. So then what I can do is I can pull out that x plus 1 from each of the terms. So I'll have x plus 1, and then what's going to be left from that green term? Just x squared. So let me underline that in green. And then, oopsies. Plus, and then what's going to be left from the orange underlined term? If it's 3x plus 1, and I pulled out x plus 1, all that's going to be left is that 3. There we go. So then I have x plus 1, x squared plus 3. I'm just writing it. Oh, sorry, plus 3. And I can't factor that anymore. And we'll talk about how we definitely know that we're done factoring. But that is the process of factoring by grouping. Okay, so I'll just box that. So recap of what we did. I grouped them together. So I just took the first two and the last two, and I was like, those look good. I could have done x cubed and 3x, and I could have done x squared and 3. Actually, that would have actually got me the same place. We would have pulled out an x squared plus 3 from each term. So try that if you want. It'll still work, which is pretty cool thing about grouping. I like processes in mathematics that if I jumble something up and I switch things around, but it's the same equation, and that method still works, that chef's kiss, beautiful. Love that. Because there's so many ways that you can write an equation and so many ways to do the same method. I just love that. So we pulled out, I put these little parentheses here, and then I looked at just like this as my expression, x cubed plus x squared. Okay, both of those have the greatest common factor is x squared. So when I pull that x squared out, it's kind of almost like dividing by x squared. So that's why there's a 1 left over here and not a 0. Do not put a 0 there. And similar with 3, when I pull 3 out of 3x, there's just a x left over. And if I pull the 3 out of the 3, only 1 is left over. Think about it like I'm dividing it out, okay? And then each term now is something times x squared plus something times x squared. Well, the greatest common factor of those terms is not x squared. Why am I saying that? X plus 1. Something times x1 plus something times x1. So I pull out x1 and I'm left with x squared and plus 3. And then we're done. So super fun. Okay, don't worry, we're going to do more examples. So now I said to be careful when drawing your groups when we have negatives. Because remember, we talked about distributing that negative in an early lecture. So now we just want to be a little careful because now I have some negatives involved. So this one kind of goes about my fun little rant I just talked about, because if I chose to do AW and BC literally have nothing in common. That's the only case where you might need to switch things around. So let's rewrite 2 as like AW minus BW plus BC minus AC. And that'll also take care of my negative problem. And all they did is they just switched the place of these two terms because addition and subtraction, not subtraction, addition is commutative. So A plus B is B plus A. And we can think of that negative as like incorporated into BW. Okay, great. So now I'm going to group AW minus BW plus BC minus AC. I'm not using all the colors that we did before. So I've grouped. And now I'm going to pull out GCF. So AW minus BW, the only thing they have in common is that W, so it's A minus B plus, what's common here? The C, and it's B minus, let's be a B, B minus A. So pull out GCF. Well, crap, I don't have, this is A minus B, and this is B minus A. Those aren't the same. So what I can do is pretty cool. I can pull out an additional negative. So what that means is I can write W A minus B minus C. So that would make, it switches the sign of each of the terms. So that would make negative B plus A. So even though I called my greatest common factor out, I can still also pull out a negative 1. Can always pull out a negative 1. But now, just to make it look nice, instead of writing negative B plus A, I can just say A minus B. That's the same. And then now, since I've done that, I can do I can pull out A minus B. And we're done. And then we can always double check by distributing again. So what we learned from this problem is if I don't have quite necessarily what I want from pulling out the GCF, I might have to pull out a negative as well. It doesn't mean, it's not a trick, it's not tricking you. I'm just showing you there might be an additional part of the greatest common factor that you may need to pull out, that negative, if you're getting something that looks eerily similar to your first factor. Okay? So the last way of factoring is called the AC method. And this is how to factor nearly any polynomial. If there's another way of factoring polynomials, I know some people do with like an X or something, and then they put something up here, and then here, and then I don't know. I didn't learn that. I actually didn't even learn the AC method, but this is what is in our textbook, and it's actually pretty cool. And I would definitely give it a try if you are like, I know I also learned this X thing, but it doesn't really make that much sense to me. Try the AC method. Just try it, okay? So how it works is if I want to factor ax squared plus bx plus c. So we're used to saying something x squared plus x plus some number. So a, b, and c here are just numbers, okay? So the AC method follows these 2 steps. We're going to find 2 other numbers such that they add to b and they multiply to be a times c. And then I'm going to replace this bx with d plus e and factor via grouping. So that'll give me 4 terms. All right. So let me keep this up. I hope I'm like not in the way in the picture. I probably am. So eventually you can do this in your head and practice. Until then, write out all the steps. So I have 2x squared plus 5x plus 2. So A is 2, B is 5, and C is 2. So D plus E needs to equal 5, and D times E needs to equal A times C. So 2 times 2. Okay? Which is 4. So what are some factors of 4? So things that multiply to give me 4 that will add to 5. And you might have to go through a few of these because remember, we can always plot on a negative. So like -1 and -4, that multiplies to 4. But that adds to -6, not 5. So I'm going to cancel that one out. So 4 and 1, that's obviously not 2 and 2. That adds to 4. So 4 and 1 are factors. Right? So we can say D, it doesn't matter which one. So let's call that one 4. Let's call E 1. So now it says to replace B with D plus E. So instead of 5, I'm going to write 4 plus E, 4 plus 1. So I have 2x squared plus 4 plus 1, x plus 2, which is the same as 2x squared plus 4x plus just x. You can write 1x, but it doesn't really matter. Plus 2. And now we're going to, great, so that was step 2. So this was like, call that step 1, that was step 2. And now we're going to factor via grouping, so by grouping. So I'm going to say 2x squared plus 4x plus x plus 2. So what can I pull out of 2x squared plus 4x? What's the GCF of that one? 2x, right? So I pull out 2x, and that will leave me with x plus 2. And then our second group is just x plus 2, and I can't pull anything out of that, and so we'll just leave it as x plus 2, which is great. They match. So now 2x times x plus 2 plus 1 times x plus 2. Right there, we can think of a hidden 1 right there. So now I can pull out x plus 2, and ta-da, 2x plus 1. And we just factor that. I think the AC method is super useful when A is not 1. I really do use this method when A is not 1. Factoring otherwise, you're just thinking about what multiplies to C and adds to B. But if the number in front of x squared is not 1, you have to think about that, and that becomes exponentially more difficult. So that's why I like the AC method. I truly do like it. I was very confused by it at first, and then I realized I did like it. Okay, so that's how we do that one. So recap, we found 2. I like to usually write out the first time doing these problems what A, B, and C equal. Because then I'm like, oh, I know 2 numbers need to add together to be 5 and multiply together to be that times that. So that's 4. And then I kind of run through all the factors of 4 till I get 2 that add to be 5. Okay. And then we replaced 5 with 4 plus 1. Distribute my x to each of those numbers so that I now have 4 terms. Grouping is really good when we have 4 or more terms. And then grouped them, pulled out the greatest common factor, and I finished factoring. It's pretty great. Okay. So then, oh golly. Hold on, I lost my place. There we go. Okay. So let's write what A, B, and C are. So A is 6. So we're doing 6x squared minus x minus 12. Don't forget the negatives, okay? So if A is 6, that means B is going to be -1. Good job. And C is going to be -12, okay? So that means that D plus E is going to be -1. And D times E is going to be -12 times 6, which is 60 plus 12, 72, negative 72. Negative 72. So I want to look at factors of 72 and you're like, oh my God, it's a huge number. What factors of 72? I know I need it to be -1. So I probably want, when I add them together, so I probably want those numbers to be pretty close, and definitely one of them, at least one of them has to be negative because it's negative 72. So 72 is divided by 2, it's 31. 2 and 31, very far away. That's not 31. 36. Yes. That's, if I add those together, it's nowhere near -1. So we need to think of closer factors. So if you add things together and they're divisible, and that thing you add together is divisible by 3, that number is divisible by 3. So 7 plus 2 is 9, which tells you it's also divisible by 9, and it's divisible by 3. So if I divide it by 9, this is negative 72 is -9 times 8. So we either have that DE is going to be -9, 8, or 9, -8. So that's where we go to find D plus E to narrow it down. So when I add these together, so this is like 8 minus 9, that gives me a -1, and then this one gives me a +1. So I want this one because I add them together and I get -1. So great. This is my winner, -9 and 8, or 8 minus 9. That's the same thing. So so that was step 1. Step 2, I'm going to say that 6x squared plus, because I took that negative with me, 8 minus 9x minus 12, which is the same as saying 6x squared plus 8x minus 9x minus 12. Okay? So now step 3 is factor via grouping. So 6x squared plus 8x. And then I have minus 9x minus 12. So I'm actually going to include a plus and then do minus 9x minus 12. If you want, you can pull out the negative, but you need to pull out the negative out of both terms. This just saves us a little bit of that confusion. There's no x on the 12. There we go. So I would just say plus, because plus and negative is subtracting. So we're writing the same thing here. Okay, cool. So that first term, 6x squared plus 8x, or that first group, I should say. So each of them are divisible by 2. That's it. And then x, right? And then we'll be left with 3x plus 4. Yeah. And then negative 9x minus 12 is going to be -3. And negative 9 divided by -3 is 3x. Negative 12 divided by -3 is 4. So plus 4. Okay? And we know we did something right when these two match. So that's going to give me 3x plus 4 times 2x minus 3. And I don't know about you, but looking at this, it would have taken me a really long time not using the AC method to figure out that it factored to this guy right here. Okay? So I've done 2 of my own. So now, oh, sorry. Kind of got far away. It's 5x squared minus 4x plus 3. Ooh. Sometimes I type them wrong and it makes it a lot harder, but this one's right. A spam caller, goodbye. I learned if you answer spam calls and then be like, I want to be put on the new call list, they'll call you more. They will. Don't answer them. Okay. fun. So I've done 2 of these problems now kind of pretty fast. So now what I suggest you do is pause and try to do this problem on your own. Okay? I know you're gonna be like, yeah, maybe whatever. Just try it. Okay? Just try. Um, okay, welcome back from being paused. Okay, welcome back. So the first time I recorded this for B.2, I don't know how, but the screen got stuck. So we were working on example 3 after we learned about the AC method. So we're going to keep going on and going through lecture again, and hopefully the screen is working. Okay, so quick recap to the AC method, mostly for me. D and E that add to B, so the thing in front of the coefficient in front of our x, and they need to also multiply to be the coefficient in front of x squared and our constant. So, and then I replace B with D plus E, and then I factor via grouping. All right. So in example 3, we have 15x squared minus 14x plus 3. So A would be 15, B would equal negative 14, and C would equal 3. You could not include the negative, and then you're like, when you put in 14, you just put it, then you have to distribute the negative. Just take the negative with you. I think it'll be less confusing. Okay, so I want things that multiply to be 15 times 3, which is 45, and they add to negative 14. So I usually like to do, yeah, like writing a little things like this. So what are some options? So they need to add to negative 14. So one of them, they might both be negative, honestly. Since they're going to multiply together to be 45. So, and they're going to be far apart from each other since it's negative 14. So I actually don't know the answer to this one. Just sitting here thinking of numbers. Obviously 15 and 3. And that doesn't work. Negative 15, negative 3. That adds to negative 18. So that's too big. So what about 9 and 5? Specifically negative 5 and negative 9. Negative 9 minus 5. Yeah, that equals negative 14. That's what we want. Perfect. So we'll go through again. We got 15x squared. And you can choose minus 9x, minus 5x. It's up to you. Plus 3. And I kind of already did one step where I plugged in for negative 14x, negative 9 minus 5, and distributed the x. So I did that all in one step. Okay. So then what next? I'm going to group them together. So those two, and then, so it's going to be 15x squared minus 9x plus negative 5x plus 3. I can pull out an x, and I can pull out, I think, a 3. So 3x, and then that'll leave me with 5x minus 3. And just to make, I can't really factor anything out of negative 5x plus 3 other than a negative 1. And since I can see that, well, this is a 5 and a negative 3, I am going to pull out a negative 1 just so that my factor by grouping works. All right, and then factor by grouping. So each term now has a 5x minus 3. So I'm going to pull out a 3x minus Well, this 5x minus 3 is the only thing that's left. So it's not going to be a 0. I'm basically dividing each term by 5x minus 3. So 5x minus 3 divided by 5x minus 3 is 1. So that means there's a 1 right there. And we're good to go. Just like that. Okay. So you can guess, Mackenzie, I like know how to factor, like, maybe not the last one, but like, can I just like guess all the options? Yeah, but like it's kind of hard to do that. In my opinion. You have to do like let's do this one. So like guess and check is also like trial and error. So like I know that this needs to it's 2x squared. So either one of them is going to be 2x, the other one's going to be an x, and then it needs to be things that multiply to -6, right? So think about FOIL, first, outer, inner, last. The first make this term, the last make this term, and then the outer and the inners make the middle term when you add them together. So 2 and 3, those are factors of 6, but this is -6. So one of them has to be negative. So I'm either going to have like +2, -3, or I could have -2, +3, something like that. But then I would get like 2x plus or minus 6. That's like 12x plus or minus 2x. That doesn't get me anywhere close to 11. That gives me to 10 or 14. So that's not going to work. What if I switch the 2 and the 3? I write, you know how I write plus or minus here and I write minus plus here. It just means when this is plus, this is minus. When this is minus, this is plus. They just kind of work together. But then again, I get 2x minus plus 2, which will give me a plus or minus 4 and 6. That at most will give me 7x. It doesn't get me close to adding to be 11x like I need it to. So I could also try 2x and 1x again. That's probably going to be our most stable one. So we have to think of other things that factor out of 6, like just 6 and 1. So let's do plus or minus 6, plus or minus 1, I guess minus plus. And but that gives me 2x, 6x. Not going to get me to 11x ever, no matter which way. So no, no, no. So last chance, 2x plus or minus 1, x minus plus 6. Okay, well, 2x times, let's say a positive 6, that gives me 12x. And then a minus 1, because they have to be opposite signs, because it's -6. That gets me there. Right, and then I can narrow it down to specifically being there. And that took a lot of chances. So each one of these blocks is 2 answers, right? Because I have that plus or minus. So 1, 2, 3, 4. So there was 8 possible choices right there, and one of them's right. So yeah, you can guess and check all 7 of those. Feel free. It's just gonna take you a lot of time, and I just work smarter, not harder, in my opinion. Okay. So with practice, it might be easier to see of how to narrow those down. But right now, the AC method can help you do it, especially when the number in front of x squared is not a 1. That is when I find it harder to factor. Without using the AC method. Okay, cool. So done with the AC method for right now. All right, cool. So how do we know that we finished like factoring completely, right? You're like, okay, I usually just say like, all right, we're done. But like, how do we really know? So we say that an polynomial is irreducible if it cannot be factored, right? So IR usually just negates whatever comes next, reducing it down to its factors, able, whatever. So really the word means cannot reduce more. So I can't reduce any factors. All right, and so we can say a polynomial is factored completely if it is a product of irreducible polynomials. So if each factor is irreducible, we're done factoring. All right, so quick ones like this, x squared minus 1. We'll learn this one in just a second, but this is not irreducible. This actually factors into x plus 1 and x minus 1. And we'll learn tools in C.2 to help us figure that out a little bit more. But if I set this equal to 0 and solve and I get a real number, that's a pretty good indication that it is factorable, because we talked about factoring is very useful when we're finding roots. So like x squared minus 1 equals 0. X squared equals 1. And then I know that x can be 1 and -1. I'm not saying that 1 is equal to -1 here, comma. So that's a way to like rigorously check that it is reducible, not irreducible, same thing. If I can set it to 0 and solve. It's not always true, I think, but it's a good way to show it really just for now. Okay, anyways. Ax plus b. So in this case, a and b don't have anything in common, right? B cannot be divided by a. There's no common factor. I pulled that out already, right? So if I have some random number times x plus some other number and they're not related by any factor, that is irreducible. 2x plus 4, I can reduce that. I can pull 2 back out. So that's not what we're talking about in that case. Well, there we go. What about x squared plus 1? Look at x squared minus 1 and x squared plus 1. Well, now, I don't know. So x squared plus 1, I kind of already said this. That would be x squared equals to -1. I take the square root of -1. Gross, I can't do that. So this one is irreducible. Its roots are -I and I, which is, those are imaginary numbers. We don't deal with those. For any case. Okay. So first time I recorded this lecture, I went through these two examples, but I think I'm going to wait and do them, and then we'll come back up and do it. Okay. So, special factoring formulas. Okay. So common factorizations you should know. So this guy is called the difference of squares. A squared minus b squared. Something squared minus something else squared. That factors into a plus b, a minus b. So a quick example, x squared minus 1. X is squared minus 1. 1 is squared. 1 times 1. So that would do x plus 1, x minus 1. And if sometimes you're practicing this and you want to write it down, this would be like x squared minus 1 squared. And then it's clear what a is, x, and what b is, 1. Because it's not always going to be x right there. It might be 4x. It might be 64x. I'm trying to think of other squares really fast. 121. I love 11. It's my favorite number. Something like that, right? And then these are two other special ones that are a little bit related. So a squared plus 2ab plus b squared, and a squared minus 2ab plus b squared. And the only difference is the sign in front of our second term. And that shows us the sign that's between a and b. And that's a plus b squared and a minus b squared. These don't have any fun names. Only the first one, called difference of squares. Oh, not as. And these are actually really easy to see because you have perfect squares right here and in the beginning as well. So if I don't have those perfect squares in my first or my third term, obviously it can't work. All right. So let's go back up to this first example, 2w to the fourth minus 32. First, before using this rule, I'm going to pull out my greatest common factor, which is just 2 in this case. So I'm left with w to the fourth minus 16. Okay. So then I can rewrite this as 2w squared squared. Do you see that? It's an exponent rule that when I write it like this, 2 times 2 would multiply together. And that gives me 4. And then 16 is 4 squared. Okay, so if we're looking back at my difference of squares, my a in this case is w squared and my b is 4. So this would factor into the 2 is going to stay. W squared minus 4. I should do this plus 4. W squared plus 4. W squared minus 4. Great. Now we need to check that we factor completely so everything is irreducible. Okay, 2. I can't reduce that. That's just a number. W squared plus 4. We just saw that x squared plus 1 is irreducible. So similarly, w squared plus 4 would be irreducible as well. What about w squared minus 4? Well, that's something squared, w squared minus something else that's squared, 4. So I could then write this again as w squared plus 4, w that squared minus, this is 2 squared. So then I can factor that last guy, w squared plus 4, and that gave me w, what, plus 2, and w minus 2. Ooh, excuse me. All right, so we can see that that's irreducible, and these two are also irreducible, right? Same as number 2 up here, ax plus b. In this case, a is 1 and b is either positive 2 or negative 2. And those are not, I can't pull out a common factor at all. So we're good. We're done. Let's do a few more practice with those problems. So factoring the following expression. So 4x squared minus 1. So there's no common factor for me to pull out. All right, cool. So let's rewrite 4x squared minus 1 as 2x, that quantity squared minus 1. And we can even go ahead and call that 1 squared if we really wanted to. So what's happening? Oh, I would then use my difference of squares and say that this is 2x minus 1, 2x plus 1. And we can quickly see that these are both irreducible, and we're done. Just like that. So that's a case where I don't just have a variable as I have like a number that's going along with it. All right, cool. Usually my first instinct when I see something in front of x squared is to see if I can pull that number out or some variation of it just to reduce it. So number 2, I have 4x squared minus 28x plus 49. Only 48, I don't even think 28, yeah, 28 is divisible by 4, but not 49. So I can't pull out 4x squared. So it probably has to do something similar to 1, where it was involved in the squared. So if I wanted to, I could rewrite this as 2x, not right there, squared minus 28x plus 49 is 7 squared. Great. So I have a squared and b squared like I do, get rid of all those gross things, up in 2 and 3. So I now need to make sure that I have either, most likely since there's a negative here, negative 2ab. So in this case, a would be in the sense of how I'm writing as 3 is 2x and b would equal 7. So 2ab or negative 2ab would be negative 2 times 7x, which would be 14 times 2, which would be negative 28x. Great. So this does follow the formula up here, number 3. So then I would just say, okay, 2x is my a minus 7 squared. Done. And that's it. And remember, we can always check our factoring by expanding by foiling. Okay. So we had that one other example that had like 6x to the 7th plus 6x. All right, well, let's try to do this problem. So I promise there is a method to my madness of switching all these problems around. Each one of them has a 6, and I don't really like my highest degree to have a negative, so I'm going to pull out a negative 6. So this will be x to this, oh, and each one of them has a 6 as well. So that's going to be x to the 6th minus 1. Okay? You can see there's nothing squared there. That's what you think. So then I can say that negative 6x is going to stay there. I can write x to the 6th as x cubed squared minus 1 squared. So negative 6x becomes x cubed minus 1 and x cubed plus 1. All right, well, now I have things with cubes involved and I really don't know how to deal with those. I can't really factor by grouping. There's just x squared and 1. So that doesn't help. That's where I'm going to pause on this problem, showing you the benefit of it. And then we're going to go scroll all the way down to difference and sum of cubes. So we have only difference of squares, but with cubes, it's different. We have the difference and the sum. So if I have a cubed minus b cubed, that factors into a minus b, a squared plus just ab, not 2ab. This is different than the squares. And that makes that this is irreducible, because if it was a 2 there, it would follow the special formula up top. A squared plus ab plus b squared. And sum of cubes, meaning I have a cubed plus b cubed, would equal a plus b, a squared minus ab plus ab. And you're like, that is so much to remember. If you remember the outline of I have a something b times a squared something ab something b squared, then all you need to remember, which I promise you sounds a lot, that's a lot easier to remember. You just need to remember the signs, right? So it's going to be the same sign. So there's a plus sign, and then it's going to be the opposite sign, and then it's always going to be positive. So same. Oops, let me do that in the colors I wrote it in. Same. Opposite. Always positive. Whee. Okay. And note that this is irreducible. Okay. Or else we would then factor that and we would have a different formula. Okay. So with that, I'm going to scroll all the way up here again. I'm so sorry. And I'm going to use both of them, right? I have x cubed minus 1, x cubed plus 1. Those are both the difference in the sum of cubes. 1 is a cube as well. All right, so that would be, if we're doing the first one, x, since it's a minus, it's going to be x minus 1 x squared opposite, so plus 1 times x, always positive 1 squared. For x squared plus 1, it's going to be x, same sign, so plus x squared opposite, so minus 1 times x, always positive 1 squared. And if you want to write it x minus 1, oops, get rid of those ones if you want. Ta-da! And that's how we factor it. Okay, so in that one we used difference of squares to get to here, and then negative 6x, that's, I can't reduce that anymore. I'm not going to pull out 2 or 3 or negative 6x is perfectly fine. And then I have x cubed minus 1, x cubed plus 1. And I notice that it's a difference of cubes and sum of cubes. So there's our difference of cubes. There's our sum of cubes. And then I just kind of got rid of the 1x and the squares on the ones. Make it look a little nicer. Okay, so let's do a few more examples with our difference in sum of cubes. So x cubed minus 27. What is 27 the cube of? 3? 3 squared is 9 times 3 is 27. Yeah. So this is 3 cubed. Lots of 3's going on. All right. So I know that's going to be, this is a minus sign. So this is x minus 3 because they're the same. Then x squared opposite sign. So plus 3 times x plus 3 squared. Or we can just quickly write 9. And ta-da, just like that, we factored. Really nice tools. I really like difference in sum of cubes. It's really important. We can even take it a step further. What about if 8w to the 6 plus 125z cubed? So 8 is 2 cubed, right? So this would be 2, and then this is w to the 6th. So I want it to be something to the third. So that would make that w squared. Since if I distributed at 3, it would be 2 cubed, and then w to the 2 times 3, and 2 times 3 is 6. So plus 125 is 5 cubed, and z is z cubed. So this would be 5z cubed. So, and I really like writing it like this because it really solidifies what goes in each little pocket of the formula. So it's going to be 2w squared plus 5z. Yeah. And then I want to square 2w squared. So it'll be 2w squared, that quantity squared. I already had a plus, so it's going to be the opposite. So it's a minus 2w squared times 5z, always positive, 5z squared. And then I can go ahead and clean it up a little bit. So 2 squared is 4, and that's would be w to the 4th, minus 2 times 5 is 10. Usually, yeah, let's do w squared times z plus 25. That looks like a z. 20. There we go. 25 z squared. And from that, just want to check. This I'm pretty sure is irreducible. I can't see any way of factoring that at all. Same with the second part again. There's no like further way. Okay. So with these tools, we can also, we've kind of already seen these, I can factor higher degrees of polynomials using substitution to make our lives easier. So we could have gone ahead and called like up here, like let's call A 2w squared and B 5z, and then like written out the formula and then plug the formula in. That's a way of substitution. All right. Well, what we're kind of talking about in this section now is when I have something like w to the fourth minus 6w squared minus 16. Like, I would know how to do that. That was like x squared and x, but it's w to the fourth and w squared. So what if I just let our friend x here be w squared? Then x squared, I would just square both sides. Now we get w to the fourth. So that would make w to the fourth minus 6w squared minus 16 equal x squared minus 6x minus 16. See how that substitution, this looks like a lot easier to work with? Substitution is really, really great, but it comes with a drawback, and it's only if you're not careful. So I was asked to factor the following expressions. In number one, I'm given W's. That means I need to answer in W's. My answer has to only involve W's. I'm using X in my work, and then I need to get rid of my X and put W's back in to give my final answer. Substitution is great. I just need to make sure that I substitute back in my original variable. It's like if you're ever been in not even just Spanish class, any kind of class, language class, and they're like, well, you can only speak language in that class, and then you just respond in English. Your person's going to be like, the heck? You have to only speak in the same language. In your mind, you can be thinking, oh, they're saying this in English. If they were just speaking English, they were saying this, blah, blah, blah. You can think all that in your mind, but then you need to say the final answer. Obviously, in your mind, I want you to write out your working in these classes, but that's kind of the analogy. So if we go and factor x squared minus 6x minus 16, things that multiply to negative 16 add to negative 6. Scroll down and look. My little brain is like shot right now. Excuse me. 2 and 8. Right, so what would it be? X. Who would get the negative, the 8 or the 2? 8 minus 2 is 6, yeah. Oh, negative 8 plus 2 will give me negative 6. Okay, cool. Great, but I'm not done yet. Because this answer has x's involved, but I was only given w's. So I need to look back up here and see, oh, what is w? What is x? It's w squared. So I'll say, ooh, w squared minus 8, w squared plus 2. And then you would quickly check that, okay, well, w squared plus 2, that is irreducible. W squared minus 2, that's a square, that's a cube. 8 is also not a square. Oopsies. So this is irreducible. Now we're done. Now my answer is in W's. Okay. And it's also really useful, especially in these cases where it's not just another variable, it's like a whole thing of variables. I see the most common mistake is people will expand this or FOIL it out, same thing. And then it's not very helpful. Ooh, who emailed me? I'm getting so many emails today. Oh, no one I care about. None of you guys. So let's just now call x a squared minus 3. And then x squared would just be a squared minus 3, that quantity squared, right? So up top, we would have x squared plus 7x plus 3. I think this is a million times easier to do than what we were presented. But look, this was my answer was given to me in A's, so I need to respond in A's. So once I factor this, I need to sub back in and also simplify a little bit. So x squared plus 7x plus 3. Things that multiply to 3 add to 7. Did I write this right? Sometimes I don't write problems right, and then I try really hard to figure them out. And then it is impossible. Yep, I did. What a dum-dum. This is a 12. Trying to find my color. There it is. That's 12. Okay, things that multiply to 12 and add to 7. I think this one's pretty clear. X plus 4 and x plus 3. Like Mackenzie, you just taught me this AC method. You're not even using it. Yeah, because we're trying to learn something else at the same time. I'm not going to add two things that we just learned all at once. It's great practice, but one thing at a time. Okay, but again, I need to answer in A's. So not done yet. For every x, I'm going to put a squared minus 3. So a squared minus 3 plus 4. A squared minus 3 plus 3. And then simplify. So this is a squared plus 1. Ooh, that calculation error almost messed us up. And this is just a squared. And great. And we're done. I can't factor either of these anymore. We're good to go. All right, and I think that's all. Yep, that's the last bit of this lecture. Thank you for dealing with this in 2 parts. I will see you guys in the next lecture. Have a good day.